Today's video is going to be all about fire assaying for gold and silver. We're going to talk about fluxes, we're going to get technical with chemistry, so let's get started and get some gold and silver today out of our high-grade concentrates. Here's our concentrates. These are the high-grade concentrates we're going to be working with today. They came out of a ball mill and across the table, I think. So what the customer wants to know is how much gold and silver is in this stuff. He knows the head ore is running about 1/4 ounce per ton, but he wants to know, he wants essentially me to double check for him how much gold and silver he has in his cons. He's gonna do some assays, he's gonna send them off for assay, but he asked me to run kind of a third test for him. I don't know what's in here as far as chemistry is concerned, so let's talk about fluxes and how I'm gonna mix something up and recover the gold and silver. So the first thing we have to do is we have to differentiate what we're doing today. We're dealing with high-grade concentrates. These are almost pure sulfides probably at this point, or some oxides, but it's not like we're taking a chip sample off a quartz vein and assaying them for the head ore grade. These are going to be really rich in gold and silver, and so our flux needs to reflect that. So I just wanted to get that out of the way. This is not like a head ore sample that we're going to be doing. And so my flux recipe is going to reflect that. There are 3 different types of fluxes that are very commonly used in fire assay. You have borax, you have soda ash, and you have silica sand. Each one of those chemicals does a different thing for our flux recipe. I've kind of developed a standard high sulfide flux that I've used over the years, and I've had good luck with it across the whole gambit of sulfide high-grade cons, from my mine to other mines, and I'm going to use the same flux recipe with this stuff. The first thing we're going to do is weigh out 100 grams of sample. Now there's a couple different ways to do this. I like to use 100 grams because it makes the math really easy, and because I'm doing only one smelt or assay at a time, I can use a little bit more. Typically when you do fire assays commercially, you use what's called an assay ton, and that's based on the US system in ounces per ton, but I'm trying to move towards the metric system here, so I'm going to use 100 grams. So what that will do for us is when we get our final result in our precious metal bead, we can just move that decimal place over and we'll really easily be able to see the grams per ton, per metric ton in the sample. Now, anytime you're dealing with a high sulfide concentrate, soda ash is going to be your best friend as far as the flux is concerned. This is a basic flux, and we're going to use the basic flux to absorb the sulfides, and I can talk a little bit about that here later in the video. But the soda ash is what's going to convert our sulfides from a form that's insoluble in a slag to a soluble form with the help of iron nails. And so we have about 100 grams of soda ash, a little bit less. I'm getting real exact this time. I like to match the same amount, 100 grams of soda ash, as our concentrates. So we're going to mix that together with our cons. Now this is anhydrous borax. The stuff that you buy at the grocery store is a hydrated version of borax. So when you're smelting or assaying, use anhydrous because it helps with the weight. A lot of the weight of the borax at the grocery store is water, so we don't want to do that. I add about 60 to 65 grams of borax. This will help absorb and dissolve any silica in the sample and make it much more fluid, because silica has a very high melting point and it's very viscous when at the temperatures that we get in our furnace. The other thing borax does is it's great at absorbing metallic oxides. So any oxides in that concentrate or anything that we convert to an oxide in the slag will be absorbed by the borax. It's also an acidic flux, so it will counteract our soda ash a little bit. The last major component is silica sand. Silica is similar to borax in that it absorbs metallic oxides very, very well. It's a very acidic flux, which will also counteract our soda ash a little bit. but I always like to add a little bit of silica to our flux. So now we have 100 grams of soda ash, 65 grams of borax, and about 35 grams of silica. And so in total here we have 2 parts flux to 1 part concentrates. Now we're going to mix this all up really good. We have the foundation of our smelt here all mixed up. Now we got to add kind of the seasonings, if you will, right? We're going to add some bismuth oxide here. Bismuth oxide is going to act as our collector metal. I don't know if this is 10% gold or silver, or if there's just a few little minor particles of gold and silver. And bismuth oxide is going to act as a collector. So we're going to add enough metal to the system where the bismuth can come down like rain through that flux, that slag that's melting, and collect all the little particles of gold and silver and bring them down to the bottom of that crucible. I use bismuth instead of lead because it's non-toxic, but in a classic assay, you use about 30 to 50 grams. I usually stick to about 30 grams, even with my larger amount of concentrates, because I don't need a 100-gram bismuth button that I'm going to cupel at the end. I think you get perfectly good collection with 30 grams or so. Okay, there's 30 grams. Now, why do I use bismuth oxide instead of bismuth metal? Because it's an oxide, the bismuth oxide is reactive when it comes in contact with sulfides. So this will act a little bit as an oxidizer in our smelt. So as you have the bismuth oxide and a sulfide particle in the flux, they connect, the oxygen combines with the sulfur and drives it off as SO2, and it will convert that sulfide to an oxide. So for example, if this is iron sulfide, pyrite for example, and bismuth oxide, those will connect to form SO2, iron oxide, and it will convert the bismuth to bismuth metal that will then come down through the flux and collect at the bottom, collecting gold and silver along the way. So it acts as a little bit of an oxidizer and helps eliminate some of those sulfides that we're trying to get rid of. We do not want any sulfides in our smelt at the end because it ends up with a matte layer. So you'll have a flux layer, a slag layer on top. If there's any undecomposed sulfides, you'll have a matte layer, and then you'll have your metallic button on the bottom. If you have a matte layer in there, it's essentially a failed smelt. The matte layer can absorb precious metals, it can absorb bismuth, it can absorb lead, it can absorb all the things that you're trying to collect. So the ideal smelt is a nice glassy or intermediate slag layer, and then a metallic button that separates pretty easy from the slag. The whole point of the smelt is to take all this junk that we don't want. We just want the gold and silver in here, and we got to use chemistry on this to convert all of the particles in here to be absorbed by the slag, and then all the precious metals to end up down in the bottom of the button. Now the other component that you can use, I rarely use it just because I don't think it's needed if you do the chemistry right, but I will add a little bit of potassium nitrate to this flux just as an example of another seasoning that you can use. Potassium nitrate also acts as a very strong oxidizer. So as this stuff gets hot, it releases all this oxygen into the smelt, and the oxygen combines with the sulfides, turning them to oxides and driving off the sulfur. You don't want to add too much. If you add too much of this stuff, you'll create a huge oxygen bubble or burp essentially, and you'll foam up your slag, and it can run over the top of your crucible. So I don't like to add any more than 10 to 15% of potassium nitrate to the smelt by weight of your concentrates. So we did 100 grams. I'm going to add 15 grams and cross our fingers that it does not boil over. The last thing we're going to put in is iron nails. And this gets a little bit complicated, but it essentially acts just like the oxygen does in our oxidizers that we put in. But let me write out the chemistry on a piece of paper so you get an idea of what the iron nails do. Right off the bat, I'm going to piss a bunch of people off because I'm not going to balance these. But let's say we have an iron sulfide, FeS, and it reacts with a bismuth oxide. You end up with iron oxide plus sulfur oxide as a gas plus bismuth metal. Okay, so that's how the oxidation part works. If you have a potassium nitrate, KNO, I think there's a 3 there, but we're not balancing, and it reacts with an iron sulfide, you end up with a iron oxide, a sulfur oxide as a gas, plus potassium NO something, blah, blah, blah. And this goes to the slag. So that's how we're eliminating a lot of our sulfur at the beginning through chemistry. But with the iron, what happens is, and I'm gonna balance this one because it's important to understand, when you have an iron sulfide, this is pyrite, FeS2, so there's 2 sulfur atoms for every iron atom. It is not soluble in the slag. This will not be absorbed, it will form a matte layer. But if you use enough soda ash, oh boy, sodium Na2CO3, hold on, let me look that up. And you add in iron as nails, what happens is you have the iron react with the iron sulfide to convert it to 2FeS. This is a different form of iron sulfide, which is absorbed by our slag. And when you heat up soda ash, you end up with sodium oxide plus CO2. This is why this is a gas, and this is why soda ash can froth if you heat it up too quickly, or if the slag is not fluid enough, it will bubble and boil and overflow your crucible as well. So this goes off as a gas, that's out of our crucible. And there's some reaction here, I'm not quite sure what it is, but it probably looks something like this. So I don't know, it doesn't matter, don't worry about it. These two, when they combine, these are slag soluble. There's another component to this, which we have to talk about actually, and this is getting way too complicated, and I don't know if anybody cares about this, but we're gonna flip this over and talk about this. So, iron sulfide is a very common sulfide, but there's also lead sulfide, there's copper sulfide, there's arsenic sulfide, iron sulfide, zinc sulfide. And to understand this, we have to talk about the metals reactivity chart. Iron and zinc down here are very reactive. Lead and copper are not. And so if you have an iron metal, it will rob the sulfur from these less reactive metals. You will end up with iron sulfide, which we can make soluble in our slag, and metals. So you end up with lead, copper, getting absorbed. These go into our metal button. And because they're base metals, we can oxidize them away in our Cupel. So I'm not sure if all that made sense. There's like a whole college course on this stuff, and I'm trying to combine it down into 10 minutes for you guys. But that, if you understood that, that is the basic chemistry of what's happening here. We're trying to convert all the sulfides into a form that is absorbed in our slag. We can convert all the less reactive metals to metallic form, which we can collect in our base metal button with the precious metals, and then we can get rid of all the base metals in our Cupel. How the Romans figured this out, I have no idea, because they were kind of the first ones to start Cupelling and refining precious metals this way. It's a miracle. But this is the nuts and bolts of what we're doing. Hopefully it makes sense, but now let's go melt some metal. Nice, clean, fresh crucible. I'm gonna add our charge here. That's about as full as you want a crucible, especially with stuff you have never smelted before, because this will gain volume. It might come up to here, and if you fill it right up to the brim, it will boil over. I'm gonna do something a little bit different. All that chemistry we talked about earlier is based on the iron nails being in there, and it is able to react with that. Because I've put oxidizers in there, potassium nitrate and bismuth oxide, I'm gonna let that chemistry happen first. So I'm gonna let this slag form, everything in there that's gonna oxidize, I'm gonna let it oxidize. And then once it's all fluid, I'm gonna put the iron nails in at the end, where we should have a slag. There will probably be a matte layer in here before I add the iron nails, because I don't have enough oxidizer to oxidize everything. And then a metal button at the bottom. When I add in the iron nails, the iron that comes in contact with that matte layer will react with the sulfides that are there, and it will eat the nails. These nails will get eaten real bad. They might, if there's enough sulfides in there, they will eat the whole nail, and I'll have to add more. But I'm not gonna add the iron in until after the oxidizers have done their thing. So let's get this in the furnace, get it all molten, and then we can add the iron nails later. Come on over here to our furnace. Now we'll get that fired up. Now, why don't I add the iron nails now is because the bismuth oxide that's in there and the potassium nitrate will also eat those iron nails. We'll use up some of our oxidizing power on the iron nails, which we don't want to oxidize the iron nails. We want to oxidize the sulfides. So let's let all that oxygen get released and react with the sulfides first, and then we'll add the iron nails in at the end so we don't waste a bunch of our oxidizing power on iron. I just added those iron nails and I watched them for about 30 seconds. They started dropping down into the smelt, and they were dropping by about ½ an inch, maybe 3/8 of an inch every time. So I can tell that that matte layer is about 3/8 of an inch thick, and that reaction happens really fast. There's no reason the reactions in these smelts take minutes, not hours. So a lot of times you'll read you need to leave it in for 45 minutes after it's molten or an hour after it's molten. I don't think that's true. I think these reactions happen quite quickly, just based on the iron nails thing. Those iron nails are getting eaten up, and that reaction is happening. You can see it in the flow of the slag. So I'm gonna watch those. If those iron nails sink below the surface, I'm gonna add more, but man, it's going quick. So I'm gonna leave it in probably another 10 minutes after the iron nail reaction visibly stops, and then we'll pour it. All right, we're gonna put our Cupel in the furnace to preheat. You don't wanna add your metal to a cold Cupel. So we'll get that up to about 1850 degrees. Let's see what we got here. It almost looks like there's some matte here on top of that button, but hopefully not. Oh yeah, I think we got matte there. My nails were in there the whole time. When I poured, there was still iron, and the reaction pretty much stopped, I think. So there's our metal. That's our little metal button, and then we got this iron mat layer. So we did something wrong there. Well, we got this metal. We got the furnaces already. Let me go put this button in and see what it. I'll see what it weighs first. We'll put it in the Cupel furnace and we'll see what we get. But we got to do another one because that did not work very well. Didn't work very well at all. The other thing I'm seeing here is this glass. The slag is so glassy. I think that happens when all the soda ash gets used up, essentially. And we don't have enough soda ash to absorb this iron sulfide. Now as that bismuth melts, it'll start to oxidize, and the Cupel can absorb the oxides but not metals. So it's a sponge for oxides, and the precious metal bead will be left at the very end when all the base metals oxidize. It's a tiny bead. We got a bead. What I'm going to do is I'm going to cut the amount of concentrates in half and use the same amount of flux. So I'll use 50 grams of concentrates and still use 100 grams of soda ash, 65 grams of borax, etc. We'll mix that all up and we'll try it again, with the idea being that we used up, for lack of a better term, the soda ash in the first smelt, and so having the concentrates, hopefully we will have enough to absorb all the mat. This actually might be a blessing in disguise, because I'm really curious now to see how much better the recovery will be once we get rid of the mat layer and get our full 28 or 29 gram bismuth button. If we get a much bigger button with the elimination of the mat and the metal and slag phase, that will tell us one thing, but if it goes the other way, then we will also learn something. So it's a win-win, right? Everybody wins, even though I screwed up the first one. All right, here's our first little button, and it's quite silver, so I'm gonna assume 50-50 gold and silver. 0.024 grams for our first button. So that's 0.1, that's 0.012 grams of gold, and that's an assumption. Okay, second smelt, here we go. Where'd the button go? Oh, here we go. Yeah, that looks better. Look at that. Still, the slag is pretty darn glassy, but we got slag and a metal button there. That looks way better. Yeah, let me get it cleaned up some. That's what you want. Slag and metal. All right, let's get our little button here in the furnace. Let him melt. Yeah, melts nice. This one over here is for something else. I'll tell you more about him at the end of the video, but we're focused on this one for now. Okay, let's take a look. Another fairly small bead. but it's only half the material as well. Before we talk about the final results, I wanted to give you a little sneak peek on an upcoming video. I have got tons and tons and tons of slag that I'm going to reprocess. I'm going to resmelt all of this, and that is what you saw the Cupel in the furnace was from me resmelting a test sample to figure out how much gold and silver I've lost in my slag. So stay tuned for that video. Don't forget to subscribe. That's a lot. That's a lot to deal with. But now let's go check out the results of our assay test. All right, this is our second bead here. .018. And about the same silver color. So let's go do some math. I'm not going to spend a whole lot of time here, but the first bead ends up being 120 grams per ton gold and 120 grams per ton silver. And the second smelt, where we didn't have any matte, ended up with 180 grams per ton gold and 180 grams per ton silver. Now those numbers are actually pretty close. When you're dealing with high-grade cons, there could have been a couple of larger gold pieces that got into the second smelt, even though we did less amount of concentrates. So that could throw our numbers a little bit. The moral of the story for me is these concentrates just aren't that rich. I mean, you're only talking about 4 or 5 ounces per ton of gold, which is a lot of money per ton, but if you got to process 30, 40 tons to get that, it's probably just not worth it. You need to increase the value of your cons. You need to increase the concentration ratio. You need to get that gold up. We need to get in kilograms per ton, not grams per ton. So thanks everybody for watching. We'll see you on the next video.